Hello and welcome back to Calculus 1 section 3 point something 11. There we go. Related rates part 2. So we are going to focus now on volume. And when we discuss volume, we're going to focus on 3 types of shapes. So 3 types of shapes. The first shapes are prism-like. So that would be a cylinder, cube, or a box, right? Stuff that looks like that. And the volume for these types of objects is always area of the base times the height. So area of the base times the height. Now your base for the prism could also be, let's say you have a triangle in a base and then you have a triangle on top, right? So that's a prism. You can have 5 sides, you can have 17 sides. As long as you are able to find the volume of the area of the base, you will multiply by the height of the object and you will get the volume. So the first object over there is a cylinder, right, which is like a pipe or the soda can, right? That's going to be the circle. Area of the circle on the bottom is pi r squared. And then you multiply by the height of the can to get the volume of the can. So that's the first category of objects. It bothers me, it looks disgusting, so I'm just going to fix this. So we have some kind of a box, let's say. The second category are spiky objects. I call them spiky objects. So we're going to have a cone. We're going to have a pyramid with whatever amount of sides you come up with. And those volumes are always 1/3 base times the height. So if you have a spiky object, you need to have the base. Now base could be circle, could be triangle, could be square, could be rectangle. I don't care what the base is. You have to figure out how to find the area of the base, multiply by height, and then 1/3 in front. So you see that all of those objects that are on the left, you can actually create them into spiky objects because you could have this right like that and then go into a 3-sided pyramid. It's okay, right? And that's that.
What's that thing on the right?
This one?
No, the other side.
Triangular prism.
Triangular prism is the one that is circled. This, you mean this?
Yes.
It's a prism. They're all prism. All of these things are prism. If you have, so you can have multiple sides. You can have 4 sides, 5 sides, 10 sides, and so on. Third category, populated by a single object.
Tesseract.
No, you said Krug. Wow. That's right. No, that's. So what's sphere? Ball. One object, perfect object, sits here alone. Volume is 4/3 pi r cubed. That's it. Now you know all of the volume for important shapes. So now I can come up with a snowball question or inflating or deflating spherical balloon, right? Or figuring out inflating a soccer ball or a basketball, right? Or you can put the snowball down the hill like in a cartoon, right? And it needs to smash into something, right? So as it goes down, picks up more snow and grows in volume. So you've seen that in cartoon. So a whole bunch of these things that involve the ball. So if I have, let's say, a snowball, and I want to put the snowball over here and let it roll down the hill and picks up more and more snow, right? You gotta have a target of some kind over here. I mean, come on.
Oh, that's it.
There we go. Much better. So when you have, right, you have this, you can calculate the change in volume of the snow picked up as the snowball rolls down the hill. So you will start the problem with the volume of 4 pi over 3 r cubed. You will differentiate that in time because it takes time for this snowball, right? Obviously, I mean, this person has time to move. It's not instantaneous, so, right, it happens in time. So we have dv dt is equal to 4 pi over 3r squared dr dt, because the volume is changing. The radius is changing because the snowball is becoming bigger as it's rolling down the hill.
Aren't there other factors like the wetness of the snow or any like wind factor? Or...
I will make sure to include it on your version of the test. The rest of you, don't worry about any of it.
Thank you.
So you will not be disappointed. What's your favorite color, like green or yellow? Because I need to distinguish your paper from anyone else's. All right, so the answer is yes. So we have a 4 pi r squared dr dt. And this formula here is related rates. So now you can calculate the gain in volume. If you leave the snowball to melt, well, then the change in radius is going to be negative, and you will be able to calculate the loss of volume. Or you are interested in change of radius, but you are not going to and you're not going to measure it. So what you can do is you can capture the water that melted, right? And then you have dv dt, because you will say, in 15 minutes I collected this much water, so you have milliliters in 15 minutes, and you have the rate for volume. So there is always something that you can measure and something else that you can calculate. The main part of these problems in 311 is for you to read the question carefully, think what kind of geometry you have, use appropriate formula for that geometry, differentiate to get related rates, and then from that point on is plug and pray that it will work out.
Let's give it a rate.
What happened?
Let's give it a rate
What rate?
of how big the snowball gets when it's up.
Okay, so we can do that. Do you want to do metric or imperial?
Imperial.
Imperial it is. So now, what is the radius at, let's say, right here? This is the snapshot in time. What is the radius?
3,000 miles. You gotta go hard.
You gotta go big.
You gotta go big.
So 25 inches. We said imperial units, so 25 inches, okay. And it's picking up the snow at what rate?
3,000
Stop with the 3,000.
inches, right?
So let's pick up 10 inches per minute. So we are picking up, radius is picking up 10 inches per minute. So the change in volume is going to be 4 pi, r is 25 squared times 10. So, okay, quick computing, 4 times 25, so don't square it, You you steal one of the 25s. So 25 times 4 is 100. There is a pi there. And then you have another 25, which is times 10 is 250. There we go. And now you have 25, and then, 250, and then additional 2 zeros. And then there is a pi. And this is going to be inches cubed per minute. What happened?
The 4 in front of the pi.
Yeah, I took it and multiplied into 25. Because I wrote 25 times 25, and I multiplied one 25 into 4 and the other one into 10. Because I didn't want to multiply. I mean, 25 squared is 625. It's easy, but then you have to do 625 times 4, which is 625 times 2 times 2, and it just makes it more noise than if you multiply this way. Anyway, there you go. 25,000 pi inches cubed per minute. Awesome. Exactly. All right, so let's take a look at another engineering part. We are going to have a conveyor belt coming in at the angle like this. And it's going to have some kind of product on it. Let's say it's either corn or gravel or stone. Well, I don't care what it is. It's going to veggie straws. Yeah, okay. And it's going to fall off the conveyor belt onto a conical pile. Obviously, it's going to be conical pile. What happens with this conical pile in time? It grows. Great. So it's going to get bigger, and it's going to get bigger, and it's going to get bigger. And if you are not careful, what happens? It grows so big that it gets all the way to the conveyor belt, and then this stuff is going to start piling up and then eventually break conveyor belt, which is not good. So we want to design a system that will shut off the conveyor belt at some point. Now you might say, well, just use the photo sensor and then when it reaches a certain height. Yeah, no, because there is dust to block the sensor. The bird might fly by and just, shut it off and so on. So there are a lot of issues why you do not want to use the photo sensor. And now, do you really want to hire someone who's just going to stare at it to push the button, right?
I want that job.
Twice, you would love that job, huh?
Yeah.
You push a button twice a day when it reaches a certain height, right? So we want to come up with mathematical formula which will be worked out into the controller that will turn the machinery off when we reach the certain height. So when you are looking at the cone, right? When you are looking at the cone, you know that important features of the cone are its height and its radius. You also know that the geometry is cone, and we're talking about the volume because when you are sending stuff on a conveyor belt, you are sending volume, right? You're sending stuff. So the rate at which stuff falls onto the pile is going to be given by dv dt because it's change in time, right? Change of volume in time. You can send a lot of corn at once. You can send a little bit less corn at once, right? So now we see that the geometry is volume, and we know that for volume, because it's a spiky object, is going to be 1/3. The area of the base is pi r squared, and then we have the height h for the cone. So now, if I take the derivative in respect to time of my volume equation for the cone to come up with the related rates, what do we see immediately as the issue here? What's now new with this formula that we did not have previously?
Three variables,
more variables. So how does that affect our derivative?
Product rule.
Beautiful. I have the radius which is changing, which is which is a variable, and I also have the height that is changing, which is a variable. R times age, R squared times age. Variable times a variable, that's a product rule there, so you have to be very careful with these things. Okay, so now we have a dV dt, which is change in volume in time, and guys, you know what this is because that's what's coming in on the conveyor belt, is equal to pi over 3, that's a constant. And now what do I have inside? Well, derivative of R squared times age. Copy the first, it's a product rule. Derivative of age is dH dt, plus copy the second, which is age, times derivative of the first, which is 2R dr dt. So now I have the derivative, which is my related rate. The next thing that we have to figure out, and the reason why this problem is so hard, is because we have a lot of variables to worry about. I have the rate of change of volume, the rate of change of height, the rate of change of radius. I have the radius, another radius, and the height. Holy nightmare, right? It's a lot. So how do we reduce the amount of variables, right? Well, we are going to take a look at the geometry of the cone and then use similar triangles to make the relationship between these. So if they give you that this particular cone is going to have the height of, let's say, 9, and over here the width of, let's say, 3. Let's say that's given. It could be in feet. It's okay, right? It's a pile of sand that it's growing, or pile of corn that it's growing. Nice one. At some point in time, this was smaller, right? At some point in time, it was smaller. So when you consider the similar triangles right here, you know that the long length is 9 and the long length over here is 3, but then you have the little h and the little r here for the smaller triangle. And you can write the proportion from this triangle. You can say 9 is to h what 3 is to r, and then you can cross multiply to get 9r is equal to 3h, and from there you can, let's say h equals to 3r when you divide both sides by 3. The coolest thing about this relationship, which keeps the height equal to 3 times the radius, the cool relationship is that you can differentiate that one as well in terms of time and come up with a relationship that connects dH dt with dr dt. And now you are going to plug these two up there to eliminate age from calculation. If you solve this for r and plug them in, you can eliminate r from calculation. So if we have dv dt pi over 3, open parenthesis, r squared, and now you have dh dt, well, that's 3 dr dt, plus we have 2rh, 2r, and instead of h I have 3r, and then I have dr dt. So over here, this is your dH dt, which we swapped, and this is your age. So we swapped them out for r's because we had those equations. So now dv dt is equal to pi over 3, and I have 3r squared dr dt plus 6r squared dr dt, and you see how they add as like terms. So that creates 9r squared, which cancels with a 3. So dv dt becomes pi over 3 times 9r squared dr dt, and then 9 cancels 3, for the total of dv dt is equal to 3 pi r squared, 3 pi r squared dr. Now I'm regretting this because I just realized that it would be better if we solved it for h rather than for r. And the reason is you can have a big stick in the back that tells you the height, right? But that's okay. I mean, whatever. Because you control here, with these two equations, you control whether you want to solve it for h or you want to solve it for r, because r is h over 3, and then the r dt is the h dt over 3. So you can solve for either one. I was just avoiding the fractions without thinking too much about application. It's much easier to measure the height because you can put some kind of a visual marker for the height, and then just look at. Yes?
Couldn't you put a measurement on the ground if you know exactly where the stuff is coming off the conveyor? And you just put the weight around?
You can put the measurement out, and yes. Well, I mean, it will definitely help in this case, right? The way I did the calculation. So now that we have the related rate, this rate relates the volume with the growth in radius, right? We actually wanted the height because again, dv dt is something that you have. Radius is something, as Rory said, you can just look at the ground and you see if you put the measurement on the ground. So, the conveyor belt is going to start dropping corn from here, there, and then here's the 1 feet, 2 feet, 3 feet, right? You just have, right? So you can have that, and then, but generally you want the height because you don't want it to reach all the way up to there and break it. So these are the design problems, and this is where you make money, guys, when you start working. Yes?
Could you do an example of filling up, say a silo, so you get to a certain radius and then it will stop expanding and only the height will increase?
Well, you don't care about these because you will always be conical going up, because once the bottom portion that it's filled is a cylinder, so you can just take it out. I mean, out of calculation. You only care about the cone which expanded enough to hit all the walls. So there are a whole bunch of problems that are measuring distance. So there is a distance to measure. They call it problem. One of the problems says bug on a parabola. So a bug is moving along the right side of the parabola y equal x squared at a rate that is distance from the origin is increasing at 1 centimeter per minute. So you have a parabola, you put the xy point somewhere, you connected that point to the origin, and then you just do the distance formula, you do the rates, and you have the fun. Then funniest thing is the next problem says another bug on a parabola. All right, now those of you that really care about design and you want to be actually engineer, and you've seen some of the snippets of these things, here are the challenge problems for you to break your heads, and then you can stop by and talk. Filling a pool or draining a pool. So you see that this pool, again, on this side you have 1 meter depth, that's half of me, right? On the other side you have 3 meters of depth, that's up to the ceiling. So this is a good sized pool, right? It has a nice deep end, right? And it has a shallow end. So you have a pool. You see that obviously the water on top is going to be flat. You see how it dips over here on the side in a trapezoid, right? So you can go ahead and play with that problem, see if you can figure out. Here is the problem that we just completed. Another problem that I do with, not every time, but sometimes, let's say that this guy wants to go up and clean the gutter, right? You have a 13 feet long ladder. So the guy goes up to clean the leaves. Now you sneak in, right, and just like kick the bottom out of it. How fast is he gonna hit the ground? Because when you hit this side out, that's your dx dt, the dy dt is gonna go down. This is the same. This is very similar to the airplane problem, right? Except this airplane is going down, and this one is going the same way like the other one. So you can see that problem. That's really cool. Now that problem is very easy. Here's the corn problem. Now they're draining the liquid through the conical tank, the same stuff we just did. That's solving that problem. That problem right there with a hemispherical tank. That's half of a ball. Good luck. And the fishing problem, if you're into fishing, please don't talk to me. And the two tank problem. What is that? What is this?
Cone in a cylinder?
Yeah, what is this?
A pain in the butt.
No, what application?
Hourglass. Hourglass?
No, hourglass. I know it's a hourglass. What is this?
Gas tank?
No. What is it?
My house.
Yeah, I know it's a cone in the cylinder. I know that. I'm asking for application, guys.
Great.
Come on.
It's a swimming pool. It's a very nice one.
Which swimming pool looks like this?
Oh, math club. Math club.
Oh,
It's not.
That's what we'll do.
It's telltale.
Design this, right? What is this? Come on. No and no. No. Thank you, coffee maker. Holy nightmare, people. Come on. Coffee maker. Yeah. Oh, I'm sorry, the water wasn't brown. Yeah. Coffee maker, of course it's a coffee. It's common sense, clear as day. Right? This is the part where you put the filter, you shut the water through it, and then it's just gonna go here. Right? Keep the water up there. Yeah, it's a coffee maker. Awesome.
What page is that?
Two things. I don't know, whatever.
230.
Oh, it's
No, this is the 213 old edition, not the new one.
Oh.
So that's why I'm not advertising problem number.
Lloyd. Oh my god.
And now,
You working with coffee?
you have a whole bunch of these guys. Here are your ships, which is the same as planes, but they're including the angle. Over here is the searchlight wide beam. On the cop car, you have those side beams, right? If you move it a little bit here, how much it's gonna swipe 100 feet out, right? And so on. So that's a nice one. And now, drum roll. You figure out 52? I stamp you a god over here, all right? So look at that cool thing. You're watching a Ferris wheel, and there's an observer, and then at angles, and then everything is turning. And yeah. So yeah, try to figure that one out.
He's in the parking lot just looking at the Ferris wheel. He's definitely
Yeah.
someone.
This is what mathematicians do. We just walk around and we see something interesting and we said, oh, so how will I figure that out? Right? So these are, whole bunch of things. I mean, this one is also really interesting, but you are going to get much easier way of solving this in Calc2. It still can be done here, but it's not easy at all because you have the half of the circle over here, and every time the water goes down, it goes flat. So yeah, good luck. So you see what these problems actually look like. Here is also viewing angle. I actually did this for my personal theater to position exactly where I'm going to put the chair for the best viewing experience. I'm not joking. I actually did this problem. And it actually works really, really, really nice, because if you just put it anywhere, right, then you're either gonna, the people go to the movie theater, they sit in the first row, and then they spend the entire movie doing this, and they wonder why their neck hurts next day, right? You just sit at least a row, halfway back, so you don't have to do that.
Row H is good.
Well, it depends which one. And that's related rates. So that's related rates. You have a whole bunch of these challenge problems to consider at the end, and you are going to have one or two of these on your next exam, which you will apparently vote on Tuesday. So start doing stuff. Bye.